Paste a long, ugly link in, get a tiny one back. Click the tiny one, you are there. 2 seconds feels like nothing. But behind that nothing is a system taking billions of clicks. And here is the one idea I want you to leave with. A real system isn't clever, it's a stack of trade offs, and the numbers decide everyone. Let's build it. Before any boxes, what does this thing actually have to do? 5 answers, and every box we draw later has to prove it belongs. 1. Take a long URL, give back a short code. Number 2. Take the code, send them to the original link, and it has to feel instant. Nobody waits on a redirect. Now, here is where the whole design changes. Think about it. You share one link, and hundreds of people click it. So it's very one sided, roughly 100 clicks for every link created. Remember that number, it decides almost everything later. Next, it has to stay up, and the codes cannot be easy to get. You shouldn't be able to take one code, add one to it, and land on someone else's link. Hold that thought, it matters a lot later. And one that's easy to forget. In the real world, we also have to count every click and survive people trying to abuse it. Miss these, and you have built a demo, not a real product. Quick numbers, not math for its own sake. Each one forces a decision in about a minute. 100 million new links a month is about 40 writes a second. That's tiny. Honestly, a single machine could handle that writes easily. But 100 reads for every write, that's a few thousand reads a second. And a viral link goes far beyond that. So look at the gap. Reads are 100 times than writes. That gap is the whole design. Half a kilobyte a link, 100 million a month, terabytes in few years. Too big for one machine to hold. Keep that in mind. And the code themselves, 62 characters, 7 long is 3.5 trillion. Decades of room, so 7 character codes. And if you're wondering why 7 not 6, 6 is already tens of billions, more than enough. 7 just gives us comfortable room. Okay, enough math, let's design. This is the full production system all at once. Don't try to read it, I am showing it so nothing surprises you later. We will learn every box one decision at a time. And one honest thing first, at our numbers 40 writes, a few thousand reads a second, a single server with one database would cope just fine. We are not building for the average, we are building for the viral spike and a few years of growth. So keep one thing in mind as we go, nearly every hard decision here comes back to those reads. Start at the very front before a request even reaches our code. A few systems prepare the way. DNS points the users to the nearest server. The CDN handles sudden traffic spikes and secure handshake. A rate limiter throws away the obvious abuse, and a load balancer spreads the traffic evenly. None of this is clever, it's all just so heavy traffic never reaches the core. Behind it, one front door, the gateway. We could make every service check your login itself, but then code lives in the 5 places and every service faces the open internet. So we check once here and route from here. One place to lockdown. Now the first real decision. Making a link and following a link look similar, but they are very different. One happens 40 times a second, the other thousands. Put them on the same servers, and one viral link slows down link creation too. So we split them, a write path and a redirect path, and scale each one on its own. For a big spike, we just add 100 redirect servers. The right side is not affected at all. The right side does one small extra check. If someone is trying to shorten a known bad link, a scam or a malware site, we reject it right there. Then it asks a small ID service for actual code. And that ID service, that's the hardest part of this whole system. Hold on to that, we will come back to it once we have finished the picture. Now, the part everything has been pointing to, the data. We keep saying reads dominate, so let's actually ask what becomes expensive here. The CPU, not really. The network, also not. It's the database. Every single click turns into disk lookup, and the disk is where it starts breaking. So the first step is obvious, keep most reads from ever reaching it. Redis sits in front, holding the popular links in memory. Microseconds, not disk. And real traffic is very uneven. So most clicks stop right here and never reach the store. That's the main idea. The database is expensive part. So we do everything to keep clicks away from it. Behind it, the store itself, one code in, one URL out. No joins, nothing rational. Honestly, I wouldn't even reach for SQL here. That is exactly what a key value store is built for. We split it by code. This is called sharding. So any lookup hits just one machine. And notice how we split for size, not speed. 40 writes a second is nothing. The terabytes are the real problem. Each shard is copied onto extra machines, replicated. And since reads dominate, those copies serve the clicks. One last catch. A brand new link could be read before its copy is ready. So the write adds it to the cache straight away. And the first click is still a hit. One thing still left on the read path, counting clicks. Every redirect has to be counted, but the catch is counting adds even a few milliseconds. Every redirect gets slower, and fast is the only thing we promised, so we don't count it on the way. The redirect drops a small note onto Kafka and sends the user off. Gone. A worker counts it later, send it and move on. And wrapped around all of it, metrics, logs, traces. Not exciting, but when something breaks at 2 in the morning, this is how you find which box and why before the users do. You skip this on a slide, you never skip it in production. Step back, every box we just walked through came from a single number or a single promise. The read flood, the terabytes, stay up, stay fast. Now, the one box I call the hard part, actually making the code. Now, the part that is actually hard and the part I got wrong the first time I have tried this. Every new link needs a fresh code. How do you make one? The obvious idea is hashing. That's what I reached for first, and it went wrong. Hash the URL, take 7 characters, looks fine. Until two different links hash to the same code. Now every write has to check, is this one already taken? Try again. And on a space this big, that first class shows up in about a day. So, no. Random 7 characters. Check if it is free. But that's a database read on every single create, and two servers can pick the same code at the same instant. A race condition. So, no. So, what if we flip it around? Keep a simple counter 1, 2, 3 and write that number in base 62. Just letters and digits to keep it short. And the best part, every number is different. So, every code is different. You don't check for clashes, you have made them impossible. That's the whole trick. But hold on, there is still one problem. A counter counts in order, so anyone can take a code, add one more, and go through your entire database. Remember, not guessable. So before we encode it, we scramble the number with a secret key. Still fully unique, still no clashes. But now the order is hidden. If you are curious, this scrambling has a proper name, format preserving encryption. The name is not the point, what matters is this: the code stays the same, length and shape. But with a secret key mixed in, nobody can work out the order. The full how it works is its own video. Now this sounds perfect until you ask, where does that counter actually live? That's our last problem. One shade counter, every server asking it for the next number. At 40 a second, it's fast enough. Speed isn't the issue. The real issue is every create has to make a round trip to that one place. And if it goes down even for a moment, nobody can make a link. So stop handling out one number at a time, hand out whole blocks. A server grabs a range of 0 to a million and it serves it straight from memory. No round trip per link. Server dies, you lose the rest of that block. And out of 3.5 trillion codes, nobody will ever notice. And every server gets its own block, ranges never overlapping. So two servers physically cannot pick the same code. The race we worried about gone again by design. The counter handing out blocks is used once per block, not once per link. So even if it pauses for a second, links keep actually getting created. One source of truth hardly used. One last decision, and the diagram does not even show it. It's just one small setting, but it changes how whole system behaves. When someone clicks on a short link, how do you actually send them to the real one? There are two answers, and it's a real trade-off. A 301 permanent. The browser and every proxy in between remember it. So repeat clicks never even reach you, cheap and fast. But you give up control. You cannot expire a link, you cannot take down a bad one, and you stop seeing the clicks. They are cached far away from you. A 302 temporary. Every click comes back through you. You pay for the traffic, but you keep control and you count every single click. For a real product, that's the trade you want. So personally, I would default to 302 almost every time. The catch most people miss is 301 is cached by proxies and CDNs too, not just the browser. So permanent can really mean you cannot take it back. Default to 302 unless you are certain. There it is again, whole, but it's not a diagram anymore. It's a record of decisions you just watched us make. Two paths run through it. Let's trace both fast. Making a link through the edge and gateway, check it, get a code from the ID service, scramble it, write one row to its shard, and add it to cache. Done. The link exists. Following one, edge, gateway, check Redis. A hit takes microsecond. Done. A miss reads one copy, put it in the cache, sends the link to Kafka, and forwards the user. The disk is hardly touched. And that's the idea I wanted you to leave with. Nothing here is clever for its own sake. Every box is a number or a promise. The reads, the terabytes, stay up, that's all system design really is. Trade offs decided by the numbers. And that is URL shortener, build the way you would actually run one in production. If that was helpful, subscribe. I break down one real system properly every week. And tell me which one to do next. Drop it in the comments. I am taking requests.